Our last topic is changing the variables, or the substitution if you want, in double integrals. Changing the variables in double integrals. We will take a note about more than two variables, but the examples we will show here, we probably consider only two examples. That's all. How do I say it in a nice mathematical English? Substitution. So let's use substitution. Substitute. Substitute. A lot of T's there. Okay. We know what do we do when it comes to functions of one variable. For one variable function, we know that a substitution t equals some function of f comes with a, let's call it, price. The dt is f tag x dx. And so the price is f tag. Now, before we explain how to pay this price when it comes to more than one variable, I want to first give us a motivation, maybe in a different color. Infi is the color teal as well, or something else?
I think we should finish how we started with the.
First of all, no, why should we? Why should we use substitution in the first place? As we mentioned before, the problem here in double and triple and whatever integrals and double and more integrals is the domain. When we consider the rectangular domains and then x domain, y domain, now we switch from one to another and so on. For example, let's say that our domain, we can calculate the integral over this domain, is, let's say D is all the xy points in R2, such that, I don't know, x e power of y is between 0 and 1, and y above x to the power of 3 is between 1 and 4, for example. So this domain is defined by not so trivial lines in the plane. X, y equals 0, which actually is x 0, x, y is 1, and so on. But substituting, if that's the verb, substituting, yeah. Substituting, let's call them u and v. U for x e to the power of y and v for y above x cubed will lead to leads to a rectangular domain. Speaking the language of u and v, D is pretty nice, is u between 0 and 1, and v is between 1 and 4. And calculating such integrals, as we've already seen, first of all on Sunday, but you've already seen in probability, probably. Yeah? Probability.
But
Infinitely.
it just substitute x and y, or is it not the same domain? Like this is not the same domain.
No, but the function will be a different function. The integrals will be the same, just as in one variable function. Question is, how do we do it? The question is, what is the so-called price we pay? Okay. So this is the motivation why in the first place we would like to substitute. And after we agreed on the motivation, how do we actually do it? So how do we do it in double integrals? Meaning that if we substitute, okay. Having some difficulties with this word. If we substitute x, y with expressions of new variables u and v, how do we go to du dv from dx dy? So the price is the absolute value. This is the answer, right? The absolute value of the what I called Jacobian. What is Jacobian? The determinant of the Jacobi matrix What is Jacobi matrix? Let's call it, we denote it by this nice notation. Can use the Snell's partial derivatives mentioned before. The Snell's of xy and the Snell's of uv. What is this matrix actually? It is a 2 and 2 matrix in which we write the derivatives of x and y by u and by v. So it is a 2 and 2 matrix. What did I? 22. 2. What? 2. I did say 2. What's wrong with you? X by u, x by v. And this is the matrix. It's not the determinant. All right. So secular parentheses, xu, xv, y by u and y by v. We denote the determinant of this matrix with j. And so I claim that dx dy is the absolute value of j du dv. And this is the price we pay. Now, technically speaking, we usually do not, at first place at all, at least, possess x and y as expressions of u and v. It's actually vice versa. We usually have u and v, the new variables, written as expressions of x and y. Just like in one variable functions. It's usually t, the new variable, an expression of x, the old one, and not the opposite. So let's write down the problem. The problem is
it's the partial family. It's he's asking the weird A symbol. It's the symbol for partial
derivatives. Yeah, yeah. The problem is that we usually have u and v as expressions of x and y, and not x and y as expressions of u and v.
So usually when you do partial, we usually do like partial f over partial x, which is just the partial differential for x. When
Yes.
you're doing the partial of x and y, is it the vector of x and y, or like
No, it's a matrix. It's these four different elements. It's a matrix, 2 and 2 matrix. And then we calculate its determinant. It is, let's write this explicitly. It means it's x by u multiplied by u by v minus y by u multiplied by x by v.
yeah, no, oh, x u is just differentiation of x with u, or what's the idea? The matrix, what are the elements? What do they mean?
It's derivatives of x and y by u and v. And now the problem is that we usually have u and v. We know how to calculate u by x or v by x and so on. We don't know how to calculate x by u, what is actually needed for j. So let's Sammy, what did you say? What's that weird A looking symbol thingy? The snail. Is the first of all, this is our notation. Usually we use it for the partial derivatives. I mean, it's best using this notation, but it comes to many letters. The notation of the partial of the snail is quite helpful. Okay, so what can we do? So first of all, we can find or S. We can find x and y as expressions of u and v. I mean, let's say this is our two example. One can write down that x is u divided by e to the power of y, and then put it here, and you have v, and you can solve this two equation. Finding x and y as expressions of u and v. Secondly, we can use the following theorem. We have some conditions. I'm not getting into them right now, but I will talk about them later. Want to write an example, then a couple of notes. It can be calculated as the determinant of the somewhat opposite matrix of u and v by x and y to the power of -1. Means put them in the denominator, so it is actually 1 above u by x, v by y minus u by y, v by x. And when we have u and v as expressions of x and y, then we can calculate j pretty easy. Let's do an example, and then some notes about the theorem of changing the substitution, theorem of this j minus 1, and other stuff needs to be discussed. Then we can do another example. For example, let's calculate the integral over d of 1. After we finish, I will give it some geometric interpretation, where d is the domain. In Hebrew, we say trapped. I'll say probably bounded in English. Bounded between the lines and y is x, y is 4x, xy is 1, xy is 9. In the first, how do you say ravia? For
What?
four quarters of the plane. The axis, the two axes divide the plane to four.
Or
Quarter, just a quarter? No, it's in 3 dimension is it's called octant. I know the English word for it, but yes, octant. But ravia, oh, it's called quadrant. Okay, quadrant, whatever. In the first quadrant, meaning that x and y are positive. So one can draw this domain if you like. Let's use the black for the axis. And on one hand, we have y equals x, which is something like that. And y equals 4x, which is something like that. And on the other hand, we have different color. X multiplied by 1 by y is 1, which is actually y equals 1. Right? Why aren't you writing? What? Did you see it? No, something is wrong. I know what it is. I write down the line, and then the leaks just deletes it because it's not the right pencil. The line of y equals 1 above x, which is xy equals 1, and the line of y equals 9 above x, which is the line xy equals 9, and this is the domain D. It's not really helpful knowing what or how the domain looks like, but it's sometimes nice to watch. It's yx, this is y, 4x. This is domain D. Okay, it's not really important. We need to calculate the integral of 1 over D. I'll mention later that the integral of 1 actually interpreted as the area of D, but let's finish our example and do it. In the first octant, let's save this picture. Why not? So I've already drew it, so why shouldn't I? Okay. We know that in this domain, y is between x and 4x. Mhm. And x multiplied by y is between 1 and 9. And can easily write that D is defined by the following inequalities. Divide every side here by x, you get that y above x is between 4 and 1. And as we did in our motivation in the color of teal, substituting u to be y above x and v to be x multiplied by y, you get a rectangular domain, which should be pretty easy to calculate in integral above. But what is the price we pay? This is the j we mentioned before. So, substituting u to be y above x and v to be xy leads to a rectangular domain. In the language of trees, the language of u and v, VD is pretty nice. It's u between 1 and 4, and xy between 1 and 9. And v between 1 and 9. And what is the price that we pay? We get, as we mentioned, the e is small one. The integral above over d of the function 1 is the integral from 1 to 9 and the integral from 9 to 4 of 1 multiplied by the determinant of j in absolute value du dv. This is the price we pay. dx dy is determinant of the Jacobi, which I denote with j, the absolute value du dv. Now the question is, what is j? And yet again, we don't have x and y as expressions of u and v, but we have u and v as expressions of x and y, which is totally enough for us to find j. In this case, we have j is this nice little function, and the derivative of u by x, as usual, when I have x or whatever in the denominator, I write it as x to the power minus 1. And the derivative of u by x is minus 1 jumps out as in Hebrew. And is y x to the power of minus 2 multiplied by v by y, which is x. Minus u by y is just x minus 1 multiplied by v by x, which is y. X multiplied by x minus 2, just x minus 1. So we do have 1 above minus y, minus 2 times y x to the power of minus 1. And so our integral is the following integral, and multiplying by 1. We don't need it, right? And the absolute value of j is the absolute value of this thing. And now we can see that calculating j using the opposite formula, u and v as functions of x and y, is good. But when it comes to the integral itself, we still need to express it with u and v, with our new variables. I mean, just as in lecture number, if not 1, then 2, we want to substitute some expression of x by t. We cannot have x left. The integral should be written with v, and that's all. So here we need to write it with u and v, and that's all. And here, how convenient, the expression here is just 2 times u, but it is necessary to do so. We cannot continue with x and y when we've already changed to the u dv. It is minus 2 of u. And here, because u is a positive number between 1 and 4, the absolute value just cancels the minus. We are left with 1 above 2u. And from now on, it's a pretty simple integral. We've encountered such integrals on Sunday, and you probably saw them in probability as well. Is probability fun? No. Okay. The integral of, before we finish, I mean, the main reason for the example is already behind us, the substituting. Any questions about that?
No, we just get in the end a better integral, a better pair of integrals because the domain is
Rectangular, yeah. I mean, basically the motivation is the same as in one variable functions. One to have simple integral. But in one variable function, the problematic, the one who causes problem, is the function. And here's the domain. So now the domain is, yeah, quite simpler. The integral of 1 above 2u is the half logarithm of u. Where u goes from 1 to 4. At 1, the logarithm is 0. At 4, the logarithm is 4. And for v, it's just constants. So we have half ln 4. And when it comes to a constant function, the integral is just multiplying it by the difference between the bounds. It's 9 minus 1, and the final answer is 4 ln 4x. Tell me what you ask. Why can't we do it the normal way? So look at the integral in its first raw form. We don't know how to calculate such integrals. What we learned on Sunday is integrals of rectangular domains, where x and y, or whatever the variables are called, are bounded between numbers, or x domains, where x is bounded by numbers and y is bounded by some functions of x, or y domains, vice versa, where y is bounded by numbers and x is bounded by some expressions of y. But where expressions of x and y are bounded by numbers or something else, we don't know how to calculate the integral over such domains. Now, substituting will lead to a rectangular domain, over which we know how to calculate the integral. So our motivation, why should we substitute in the first place? To get a nicer, preferably rectangular domain, or at least a domain that we know how to calculate the integral over. Any other questions? Let's see. Yeah, you were correct. You want to see what I thought just, I mean, I only see, a notification. I can't see what did he say. I feel actually right. So I thought you already know. He said cool. Oh, so some notes and then another example, and then we can move on. First of all, the integral of 1 is actually the area of D. Let's write it in a different color. For one variable functions, the integral of 1 over AB is B minus A. The integral of 1 is the length of the segment AB. So the same goes for 2 variables. The integral of 1 is the two-dimensional analog for length, which is area. And one can easily say that the triple integral of 1 over some body D is the volume of this body. And we can say it for n-dimensional integrals, but then we lose the geometric intuitive interpretation. So the integral of 1 is actually the area of this. So what this question can be asked as calculate the area of the domain bounded between blah blah blah. So the last example can be asked. Calculate the area of blah 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 blah. So that's one note I wanted us to note. Secondly, something else. It happened here, but it happens a lot, so I want to write down explicitly. Maybe you've already seen it in probability. If the domain is rectangular, x between a and b, y between c and d, and the function f can be variable in Hebrew variable separated, meaning that you can write f as the multiplication of function of x and function of y, then the double integral over d of f can be calculated as the multiplication of the integral of x and the integral of y. For example, let's say we have the integral between 1 and 0 and the integral between 1 and 2, for example, of the function x squared y third. Okay, so we can, the function is separable. You can write it as x squared multiplied by y third, so it is the integral between 1 and 0 of x squared multiplied by the integral between 0 and 2 of y cubed, whatever this integral is. Specifically here, it happened with 1 as the function of v, because v is does not appear here in this integral. Sometimes it's good. It helps us to calculate integral shortly, simultaneously for x and y. So this is b. What do I want to say about c? Formally, the substituting requires no, something missing. How do it require? That's why? No. What? Require?
Yeah.
It's okay. Require. The subject requires the change of variables to be injective, to be one-to-one. And for example, here we have function of two variables. The function takes x and y to y above x and xy. Need to explain why is negative. Says in our example, the change x and y goes to y above x and xy should be injective. Now, on one hand, it's not pretty, in this specific case at least, it's not really difficult to assure that. I mean, assuming that y1 above x1, x1 y1 equals y2 above x2, x2 y2, and concluding from there that x1 is x2 and y1 is y2, a definition of a one-to-one function. But mathematically, I mean, formally speaking, you cannot substitute whatever you like. And I want to emphasize that. I mean, we mentioned it when we discussed definite integrals of one variable functions. We first encountered the substituting method for indefinite integrals. So it was pretty trivial that we are not going to substitute fx to be 0 and the integral be 0. It's not the antiderivative of the function. But when it comes to definite integrals, something is missing from the explanation. Why shouldn't we substitute t equals 0 and now the integral becomes 0? Why shouldn't? What is wrong with that? I mean, saying, okay, it's the wrong answer is not enough. If we get the wrong answer, something is wrong in the way as well. So why is wrong in the way? The substitution should be injected. And as I said, in the integrals of one variable functions, you should, when you try to calculate the definite integral, you should move to the indefinite one, find the antiderivative, however you like, and then apply the fundamental theorem, FB minus FA. But here, we don't use indefinite integrals to calculate the definite ones, or at least in first place. I mean, when it comes to the integrals of u of v, then we do it the same. Yes, the integral of 1 above u is ln u and so on. So we need a theorem that knows how to substitute in the definite integrals themselves without going to the indefinite integrals and then coming back. Now, I'm not going to write down this theorem. I'm just, as a note, know that the function of variable change should be injective. Don't be not afraid. I don't want you to, when it comes to the final exam, I don't want you, when you encounter such a question, I don't want you to explain why the change is injective. But just know that formally, it should be injective. And moreover, let's see my last note. Similarly, using this way to calculate J by the opposite of U by X and so on only holds when the change of variables is injective. It is called the inverse function theorem. If you were to study mathematics instead of computer science, then you would have studied Infi 3. And in Infi 3, we teach them, I mean, it's been some years. So last time I taught it, I think it was 4 years ago, maybe. In Infi number 3 for mathematicians, we teach them how to do it very formally and so on with the inverse function theorem and another theorem called the implicit function theorem. It's not really important right now. Yet again, I'm not expecting you to explain in a test, in the final exam, and not to me, not to someone else, why the substitution is injective, just substitute and solve. And that's it. But formally, I think it's important to acknowledge the fact that it is not so trivial. Just as we said about the Lagrange multipliers and the Weierstrass theorem for modern variable before that, they all have conditions. They are not always true, but we As we said in this last 3 weeks, the last session of the semester, we talk technical, we do not talk theoretical, which is enough. Okay. Any questions about that? Okay. So let's go for another example. Let's talk about the okay, well, I think we can move to the polar coordinates. Yes. Let's write polar coordinates to examples. Let's talk about the exam, and then if we have much time, we'll do another example for that general substituting. Substituting. Okay, so polar coordinates. I don't remember, did we mention them when we talked about limits? I think we did. Sunday 2 weeks ago. I think we talked about lecture number 20 about polar coordinates at the end for calculating limits. Yes, we mentioned Baruch Baruch 3 limits. And you can see everything in the notes. But now we can use them for calculating integrals. So first of all, what are the polar coordinates? The substitution is x is r cosinus theta and y is r sinus theta. Geometrically speaking, as we've already seen them in lecture number 20, and we are probably familiar with them from the basic of complex numbers. If we have a point xy here, we use two geometric aspects of the point to define it. One, x, is the distance between the point and the y-axis, and while x is negative, is to the left. And the second one, y, is the distance between the point and the x-axis. And y is negative, it's under the axis. Now we can change them for two different geometric aspects. One is the distance from the origin, which is denoted by r, and the second one is the angle between the vector of the point and the positive part of the x-axis. And by Pythagoras, or the basic trigonometric definitions, x is r multiplied by cosinus theta, and y is r multiplied by sinus theta. The circle with line inside is called theta. Okay, it's a Greek letter. Now, as I said, it's not very important, but you should be convinced that this is an injective substitution. I mean, if you know r and you know theta, you will have the specific point xy. As long as you know that the angle and the distance from the origin, you will have only one specific point. On the other hand, while describing the plane with x and y, the Cartesian coordinates, requires x and y to be any number between minus infinity and infinity, when it comes to r and theta, and the general, and all R2, and all of R2 is covered with, is described with, R is a positive number. The distance from the origin cannot be negative. And because sinus and cosinus have their own cycles, it is enough to look at theta at some segment of length 2 pi. Usually use 0 to 2 pi, but if you use minus pi to pi, it's basically the same. Where should we use the polar coordinates, the polar substitution, and what is the price? What is the Jacobian we pay here? So, when should we try to use the polar coordinates when the domain is part of a disk or a circle, whatever, and it can be the disk, all the disk as well. Usually, when it comes to part of a disk, using the polar coordinates will lead to a rectangular domain. In this case, what is J? And here, X and Y are actually expressions of R and theta, so we can use the straightforward formula for J and not the so-called inverse function theorem. X by R, X by theta, Y by R, Y by theta. Which leads to, okay, XR, Y theta, minus YR, X theta. X by R is cosinus theta, multiplied by Y by theta, which is R cosinus, minus Y by R is sinus theta, multiplied by X by theta, which is minus R sinus. We have R cosinus theta squared, minus minus is plus, R sinus theta squared. And we know, I hope so, that sinus squared and cosinus squared are just one. So we are left with, in the bottom line, with R. This is Jacobian for the polar coordinates. And if you need to use it in the final exam, just write R without the explanation. It's already fine. Okay, let's do an example, and I think we'll have time for another one. And then we can talk about the exam and go each one his own way. It's your last class today? Or you have something else? Data structures? Whatever. So A. First of all, for A, let's calculate the following integral. Integral over d of xy dx dy, where d is all the points xy in the plane, such that x is non-negative, y is non-negative, and x squared plus y squared is bounded between 4 and 9. We can draw this domain, and again, it is not important nor necessary, probably not even helpful. Let's see. Calculating the integral. I look at the first quadrant because x and y are not negative, and we know, and if we don't, it's time to know that x squared plus y squared equals 4 is the circle of radius 2, because x squared plus y squared is r squared. I write down explicitly, and for 9, it is of radius 3, and this is our nice little domain D. Here it is 3, here it is 2, and this is circle. It's 2 and 3 on the y-axis as well. As we said before, we've already drew. Whatever you said. Why shouldn't we copy and paste it? Oh, didn't we scale the first picture we do? I don't think so. No, 16 is allowed. Let's go with 10, 5, something. No, we didn't scale it. Let's go with 10, 4. Will be visible. Basically enough. Oh, what I mentioned, you said is I want to write down here explicitly. The Jacobian is R, and moreover, or in addition, x squared plus y squared, it's r squared, the sinus and cosinus cancel each other or becoming one, so it is r squared. Okay. Now we can see that D is a part of a disk, but without the drawing, without the paint. We know that, and we should know that x squared plus y squared is describing a circle. So we need to think, okay, we should use the polar coordinates. What happens when we use the polar coordinates? So D is a part of the circle. So we use the polar coordinates. And again, x is r cosinus theta, and y is r sinus theta. How can we write D with r and theta? The domain becomes first of all, let's write it down. If you have x squared plus y squared between 4 and 9, then yet again, x squared plus y squared is r squared. So it is r squared between 4 and 9, which is r between 2 and 3. Remember that r is a positive number. So we're not afraid of r between -2 and minus 3 or something like that. And what about x and y being non-negative? Means that r cos and r sin are greater than 0, and from the basic domain between 0 and 2 pi, where is cosinus positive, where is sinus positive? So cosinus is positive for an angle between 0 and half a pi, and, or probably should use the or sign, angle between 3.5 pi and 2 pi, while sinus is positive, yet again, from the domain, the basic domain between 0 and 2 pi. In this domain, sinus is positive when theta is between 0 and pi. And if we want cosinus and sinus to be simultaneously positive, we get that the theta should be between 0 and half a pi. From the geometric point of view, one can say, you know what? It's only the first quadrant, right? The whole disk is 1 to 2 pi. So quarter of 2 pi is half a pi. So the angle is between 0 and half a pi. But we don't need, as I mentioned, to use geometry. We don't need to draw anything, just the inequalities as we are given. Okay, so theta is between 0 and pi above 2, and the Jacobian is r, as we mentioned before, and we have the integral becoming the integral between 0 and half a pi. No. This for theta. The integral between 2 and, no, 2, yes, 2 and 3 for r. X is r cosinus. Y is r sinus. The Jacobian is r. The r, d theta. And this is the integral over rectangular domain we need to calculate. So again, the main reason for the example, substituting is already behind us. We've substituted correctly, I hope. But if we are here, well, let's finish the calculation, give a number, the result. Before that, any questions about the substituting, about the polar coordinates?
No, basically it's a quarter of not quarter of a circle, it's like part of a circle. So because we're looking at polar coordinates, it's just a rectangle, right? It's just like
Yes, usually looking at, I mean, what part? I mean, you can take a circle and then just draw something weird inside it, won't be nice, even in polar coordinates. But parts of circles, quarter of circles, some annulus, so on, will be usually described more easier in the polar coordinates. Any other questions? Okay, so now we got the situation we mentioned before when we took some notes. The function is separable, so we can write it as the integral of the theta function, which is sinus cosinus, as far as I can see, multiplied by the integral of the r function, which is r cubed dr. Now, both integrals are, well, the first one, the left one is not immediate, but we know how to calculate it. One can substitute t to be sinus theta, t to be cosinus theta, or probably the easiest way is to use the trigonometric identity of double angle, which is sinus 2 theta above 2. And here we know how to calculate both integrals, as I mentioned. The integral of sinus is minus cosinus. And yet again, we have some half here multiplied by minus cosinus 2 theta above 2. We need to put theta to be half and 2 pi. Multiply it by r to the power of 4 over 4 between 2 and 3. Okay. So cosinus pi is minus 1. With the minus, it's actually 1. Minus minus is plus. Cosinus 0, which is 1, so it is 2. So it's half above 2 over 2 multiplied by 3 to the power 4 is 81. Minus to the power of 4, which is 16. Above 4, so we are finished with 65 over 8. Whatever. Any questions about our integral?
we just separated it to two integrals, so r and theta are independent.
Yeah, the function is what I call separable. we can separate it to function of r multiplied by function by theta. If the function is so-called separable and the domain is rectangular, we can calculate it using the multiplication of the corresponding integrals. Any other questions? Okay, so let's go for another example for the polar coordinates, and then talk about the exam when you can call it a day. We have a different example here. So is this, for example, A, so this will be example B. We calculate the volume of the body bounded beneath, under the graph of xy, which is x squared plus y squared, and above the disk x squared plus y squared is smaller than 9. So, as we mentioned in Sunday, geometrically speaking, the integral of the function describes this volume. As the integral of one variable function describes the area between its graph and the x-axis, the double integral of f of a function of two variables describes the volume between f and the circle. I mean, I won't draw it pretty good, but let's say we have the circle here and we have the graph above it, some three-dimensional graph. So between this bowl and the circle, there is some volume bounded. Want to calculate it, and it's basically simply the integral of f. And because f greater than 0, the volume can be calculated by or with, and let's call it v, that's volume, the double integral over d of f. Now, it's a small point, but let's say it out loud. We use polar coordinates, and that's why, not because of the function. Yes, the function looks like a function that will look better in polar coordinates, but it's not important. What's important is the domain. Because the domain is part of a disk, it's actually the disk itself, we use polar coordinates. Because so the domain is a disk, so we should use, so we try, yeah, polar coordinates. Yet again, x is 0, blah, blah, blah. We know that x squared plus y squared, whatever. X squared plus y squared is r squared. And our disk becomes x squared plus y squared more than 9. It's actually r squared smaller than 9. And remember that r is a positive number, so r is between 0 and 3. It's the whole disk. Don't have any other inequality, any other limitation, or whatever. We do not have any other conditions. So we look at all the basic domain of theta between 0 and 2 pi. And again, The absolute value of the Jacobian is R. We have integral here. Function is x squared plus y squared. It becomes the integral from 0 to 2 pi, the integral from, what is it, 0 and 3 of r squared multiplied by r, Jacobian, dr d theta. Let's do it quickly. The integral for theta, we do not have any theta, so it's just the difference between the bounds of theta, as we know, what we mentioned before. No. That part. And the integral of r third is r to the power q of 4. Yeah. With 0 and 3, well, at 0, it's just 0. At 3, it's 81. And with this 2 pi here and the 4 there, we are finished with 81 pi above 2. Whatever units we use to describe this area.
Can you generalize polar coordinates to all coordinates with a different, possibly more trigonometric functions exist or not?
For more than 2 variables, you mean?
Yeah.
It is possible, yes. For in more than one way, I mean, what is the generalization of a disk to 3 dimensions?
I mean, is it a sphere or not?
It can be a ball. It's the probably most natural way to do it. Or I can say, you know what, we can generalize a disk to a cylinder. Well, a cylinder is basically the same, but when it comes to a ball, we do have spherical coordinates.
What function do you use, or do you not use sine and cosine?
No, you use them, but in order to define a point using the angles in the space, in 3-dimensional space, you need r, and you need two angles. 2 angles. I mean, you need the distance from the origin, and you need the, let's say, the left to right angle and the up to down angle.
Oh, okay.
If
I thought you maybe could do it with another function, but that function probably doesn't exist. Like in addition to sine and cosine.
No, sine and cosine are fine. They will suffice.
No, yeah, I mean with a single angle.
A single function.
A single angle. No.
No. But two are enough. You don't need 3, which is good. And one can generalize that to n-dimensional ball. It's r and n-1 angles, doing some nasty go around. But geometrically speaking, one cannot actually imagine it, right? Okay. Any other questions about the exam?
The exam?
About the
Oh, okay.
The material. Okay. Okay, so Sammy, any question? Okay, so about the exam, cool. No, what to do? All good. Okay, yeah, you can see it. Well, I need to check myself or check myself. Okay, for about the exam. Well, basically the same as I said about linear algebra. When does the exam actually? It's the 16th of February. Of February. Am I correct?
Yeah, different.
There's a 12, yeah, they're close to each other. Well, it will be 5 questions. Each question's 21 points. I'll try to divide the material between the question as it will divide it between the lectures through the exam. I mean, one part of question is indefinite integral, one is a definite, then the improper integrals, and so on. And of course, it won't be exact, but it will be fine. When it comes to the multivariable calculus, the questions will be very technical, just as we did here in the lecture and the practice. Moreover, all the questions for all the subjects of the course will be similar to questions we've encountered through the lectures, the practice, the homework. Just as I said, in linear algebra, you can enter a calculator. There is no formula sheet unless you have the specific permissions to do so, permits to do so. And then you don't get whatever you want. You talk to me and I give you some formula sheet to use. What else? Any questions about the exam? And again, I recommend to, go over the lectures and practices, not very thoroughly. And then you should solve the homework, and then solve past exams. If you solved all the past exams of the last 3 years, which again should be something like 12 exams, 12 for each semester, 2 for each semester, you should be fine. Should be prepared. Okay, any other questions?
Yeah, I think this you do prepare exams for, so you just do your past exams.
Yes, I mean linear algebra as well. Use the past example of AD if you want. It's totally fine. My past exams are, of course, as good or even better. And I mentioned you through the semester. Because of the snitches, the most of the questions were not recycled. Will not. I mean, still didn't write the exams, but I should do it in the next days. But they will be similar to the questions you've already encountered this semester in your homework and so on. So you won't be surprised. Hopefully, you won't be surprised. Here, I'm not saying it will be, but the exam can be the same as the Hebrew exam. Don't know if it matters to anything, but just for you to know. Any other questions? Oh, okay, so you can finish. Sammy, you stay safe, stay well. Good luck in the exam season, whatever you say it in English.